Muy buenos días a todos. Gracias por atender este seminario. Mi nombre es Juan Carlos Luna. Estoy con Brendan Brady. En unos minutitos comenzaremos. Por favor, déjenme saber si hay problemas con el audio y están invitados a hacer preguntas y comentarios dentro de la ventana de chat y preguntas.
Okay, hello everyone. My name is Brendan Brady. I am a sales engineer from Applied Analytics. Applied Analytics has been in business for over 25 years outside of Boston, Massachusetts in the USA. Applied Analytics designs and manufactures process analyzers. These process analyzers are typically designed to measure a chemical concentration of a specified chemical, like H2S or SO2 or chlorine or something like that. These analyzers can also be used to measure physical things, physical parameters such as color, transmittance, and purity, and things like that. So Applied Analytics recently got a distributor, an exclusive distributor in Mexico called Sika, and I will hand the mic over to Carlos to introduce Sika.
Muy buenos días a todos. Como dije hace unos minutitos, mi nombre es Juan Carlos Luna. Soy el gerente comercial en México de Applied Analytics. Estoy aquí con Brendan Brady. Con mucho gusto invitándolo desde Boston para dar una presentación acerca de la ley Beer-Lambert, la cual es una ley de la naturaleza expresada en términos matemáticos que ellos utilizan para sus productos de alta tecnología. Applied Analytics es una empresa enfocada en las soluciones para aplicaciones de proceso y Sika es su representante en México, como mencionó Brendan. Sika es una empresa dedicada al servicio y la venta de equipos, igual de alta tecnología para la medición. Tenemos varias aplicaciones y una de nuestras marcas es Applied Analytics, que para nosotros representa una gran solución que queremos compartir con nuestros clientes para aplicaciones online. Tenemos 27 años de experiencia en el mercado. Por favor, cualquier pregunta, esta presentación va a ser en inglés, pero las láminas van a ser en español y si tienen cualquier duda o pregunta o comentario, no duden en ponerlo en la casilla de preguntas y chat para que se les responda en brevedad. Entonces, le cedo la palabra a Brendan Brady, quien presentará esta presentación con duración de 1 hora. Gracias.
So just before I begin, clearly I'm an English speaker and this presentation is in Spanish, so bear with me. So this presentation, we're going to be going over, I'll be introducing our company, our products, and our capabilities. We'll talk about our actual detector, which is the spectrometer. We'll look at different readings of what the analyzer would actually be outputting. And we will also be looking at different applications where our analyzers fit well. And we'll look at the products as well at the end. So like I mentioned before, our detector, our spectrometer, is based off of the mathematical law of Beer-Lambert's law, which basically says that absorbance and concentration are correlated. Of course, there's different variables in correlating these two things. For example, there's light intensity, there's distance of path length, but here you can see where we measure for the light intensity exiting the sample, which would be I. So that's sort of what the detector is actually doing. It's sending a light intensity into a flow cell where it interacts with the sample, and then the light intensity coming out is what is the first thing basically being calculated. So here you can see how the absorption is calculated by using the light intensity going into the sample, the light intensity going out of the sample, and the distance of the flow cell. So it's basically just absorbance is equal to the log of the light intensity going in over the light intensity coming out. and we are able to express this absorption value as a concentration by using this next equation you see here. You can see there's a constant, that's the extinction coefficient. That's a given at each wavelength for each chemical. So that's a given, that's a constant. The D is the distance of the path length. Sometimes we have very, very short path lengths. So say, for example, you're measuring a high H2S application. H2S has a lot of absorbance, so you don't need a long flow cell. So we'd use, like a 2 millimeter flow cell or something like that. If we're going down to low concentrations, we're going to go up to a long flow cell. So the D and the distance of flow cell matters when calculating concentration. So this sort of goes over what I've been sort of mentioning. It shows how you can calculate your absorption, which is what the spectrometer does, and then you can correlate that to a chemical concentration. And of course, there's a lot of control necessary. You need to control your light intensity going in. Your light intensity coming out is something that is observed by the diode array, which is housed in the spectrometer, which I'll get to later. You also need to control the distance, like I said, and you need to know your extinction coefficients. Moving on, there is, so absorption is basically represents how much light was absorbed after it goes through the sample, and transmittance is basically, or percent transmittance is basically the amount of light that successfully passes through the sample. So say you just send a light through the air and it doesn't interact with any chemicals, it's going to be 100% transmission. So this is a physical parameter. It's kind of measuring like a purity. So a common application here would be measuring MEG, transmittance, or something like that. And you can see down on the bottom, absorbance and transmittance are also easily correlated. In this slide you see here, it's basically showing some mathematical proof behind Beer-Lambert's law. It's basically just the mathematical proof behind solving for a chemical concentration and getting that chemical concentration through an absorbance. So some important things to note. Absorbance and concentration change proportionally. We know that. So basically, if the absorption is changing from the spectrometer reading, the chemical concentration will change along with that. So all chemicals have a given molecular absorbance coefficient. Like I said, the extinction coefficient is a given at each wavelength integer for each chemical. The temperature and pressure are important conditions to consider while conditioning the sample to be measured. For example, pressure is relatively similar to length of flow cell in a way, because the higher the pressure, the more molecules you can pack into the flow cell. So pressure can affect your accuracy in a good way and in a bad way. So you increase your pressure, you can increase your lower detective limit because you're packing more molecules into the flow cell, which means you're getting more absorption. What else? Yeah, and then lastly, another important note is the distance of the flow cell is always an important thing to consider. So in this slide here, we'll go over a little bit of the spectrometer. and what you see right now is the optical assembly. So basically, the xenon light is pulsed, and that light travels through fiber optic cables where it meets what we call a collimator, which is basically an optical lens which focuses or narrows your light beam. The beam then travels through the flow cell where the sample is constantly flowing, and the light then exits the flow cell and goes back into the spectrometer where the light is dispersed onto a diode array, which is basically your detector. This is what the NOVA 2 spectrometer actually looks like. In the optical assembly, the xenon lamp and the holographic grating and diode array are housed in the spectrometer. The spectrometer then communicates with the HMI. The HMI basically, runs your software. It controls your spectrometer and produces your data. Your HMI is a touch screen that's Windows 10 controlled. On the back of the HMI is an I/O board, which basically has your inputs and outputs going to and coming from. What else? So here you can see some different readings of what the spectrometer will show you. These are different outputs. So with our analyzers, you can get numerical outputs. You can get like a numerical chemical concentration. You can also get plots like this. And as you can see, every chemical is a very unique and very structured absorbance curve. And so since they're all unique and pretty structured, we're able to observe the absorbance spectrum from a sample, and we're able to deconvolute, say, a total absorbance into speciated chemical absorbance spectrums. You also get the full spectrum here. So like you can see, you get a measurement from 200 to, here only shows 700. We go up to 800. And having the full spectrum analysis, as opposed to, say, a photometer, which is like a more traditional, simpler technology where you only get one wavelength. With the spectrometer, you get the full spectrum. So you get data points, or you get data at every single wavelength integer. So what that does is it gives you flexibility in calibration. It gives you the ability to add a measurement in the field. So say, you had an analyzer out there measuring SO2 and you wanted to add a H2S measurement to it, you could do that. You could calibrate for that because you're already measuring in the full spectrum. So multi-component analysis. As you can see here, you can see the H2S curve in blue, the SO2 curve in yellow, and then you can see an overall absorbance curve that's gray. And what our spectrometer does is it calculates an absorbance value at each wavelength integer. And what we're able to do is deconvolute the total absorbance into, say, speciate it into H2S and SO2, basically by just running a system of equations where you have two unknowns, two equations, and you do that, you're able to find the absorbance value at each wavelength integer throughout the calibration. So that also allows you to cross-reference your measurements. Which then brings us to the assumptions. So like I've been saying, you need to have some assumptions. You need to have some knowns to solve for your unknowns. Those assumptions are the pressure and temperature or density. We need to know the initial light intensity going into the sample. That's important, and that's always measured for each pulse of xenon light, because they say there's no degradation in the xenon light at the 5-year life, but there's some very slight degradation, but that's calculated for. So there's no worries. So the initial radiation is always known. And then distance of the is very important to consider. And for example, we go up to 600 millimeter flow cells, but so there was a application at Reliance in India where they wanted to measure chlorine at a very low ppm level, and on our LDL, our rate normally is 300 ppm or 0 to 300 ppm with a 6 ppm accuracy. So what we did for them is we added a second 600 millimeter flow cell. We basically halved the range and the accuracy. So that's something that we can work with for customers to work on different accuracies. So now we will get into some common applications of ours. I will begin with refineries and more specifically sulfur recovery units. In the next slide as well, you'll see we'll be flipping back and forth between these while I talk about sulfur recovery and refinery applications, but you can see we have a plant diagram of an SRU, and there's many different applied analytics applications shown throughout it. So to start, you have the H2S and sour gas, which is basically your feed gas into an SRU. This is typically, we're measuring percent level H2S here. So you want to know how much H2S you're putting into your amine unit, which is kind of the first part of the SRU. Just for efficiency purposes, you know how much amine you need to use, all that. So it saves you money there. There's also the acid gas measurement, which is very similar. It's usually higher percent H2S. We can go 0 to 100% H2S. It's with a plus or minus 2% full scale accuracy. So those are very similar measurements for the analyzer itself. Both very easy, pretty standard for SRUs around the world. 5% H2S applications, they are great for our equipment. And then next, and most importantly, I would say, or our most successful application or product is the tail gas analyzer, which is our TLG-837. I'll talk about the products briefly at the end, but you can see at AT6, we measure we measure H2S, SO2, and air demand. For those of you who know about the tail gas analyzer, you know this is key in an SRU. It's in every single SRU around the world. It's key for efficiency purposes. Basically, what you do in tail gas is you have to monitor the tail gas stream of the clause process to basically ensure that the ratio of H2S and SO2 is 2 to 1, because that's vital for efficiency purposes. Part of the clause is converted to elemental sulfur, which is what we do here. And the tail gas analyzer is basically maximizing that conversion rate in the clause process. It's allowing you to maximize that. And then next we have H2S and hydrogen in the TGTU, which is the tail gas treatment unit. So this is not in every single SRU. It's in most from what I've seen. It's basically a process after the tail gas process that takes all the H2S and SO2 that was not converted and recycles it back into the process. And that's pretty much what the TGTU does. And what we do in there is measure H2S and hydrogen. Those are very common applications in the TGTU. People often ask for those two things. So another application in a SRU is, and the only other application where we use the TLG is in the sulfur pit. So what are you supposed to do with all the sulfur or the liquid sulfur that you've converted and collected in your condensers? What most people do is they store it in a giant concrete pit. They keep the pit at a high temperature to allow the dissolved gases to come off. And what we do is we measure in the headspace of that pit. We measure H2S in the headspace to ensure that it never reaches its lower explosive limit. There have been times where the pit explodes and basically a giant concrete roof goes flying into the air. So what we do is we ensure that that doesn't happen. It's a safety precaution, safety measurement. And then lastly, I'm not sure if you see it here on this slide, but there's the H2S and catalyst pre-sulfiding. So this is like a pre-operations process for an SRU. Not every SRU does this, not every company does this, but basically what happens is they run large quantities of DMS through their catalytic beds. And what that does is it coats the catalyst in sulfur compounds. And basically what that does is it extends the life of the catalyst. And what we do here is we measure the breakthrough of that, mainly H2S. Moving on to the next industry, I suppose, would be H2S mitigation, H2S scavenging, H2S sweetening. So basically, say you have a stream. It's not a crude stream, it's not a petrochemical stream, but you have a stream where you need to take out H2S, but it's not as large scale as, say, an SRU. There the scrubbing or scavenging or mitigation process is working. This is becoming more and more popular. Biogas, it's becoming very popular in biogas and refining biogas or landfill gas. I've been seeing more of these stations worldwide. And next is chlor-alkali. So I mentioned that, so as you can see so far from this presentation, H2S is a very common chemical that we measure. It's our #1 measured chemical. I would say that chlorine is pretty close behind it. In the chlor-alkali process, mainly measuring high percent level of chlorine is our best application. We have many applications in it, such as measuring nitrogen trichloride or NCl3, which is it's a contaminant or in the process, and it has very lower explosive limit, so it has to be monitored basically throughout the process to ensure it doesn't get above. I'm pretty sure Mexichem recently had a VCM plant blow up because of this reason. So measuring NCl3 is important in the chlor-alkali process. We also measure NaOH. If you go to the next slide. In the chlor-alkali process, because as you know, caustic soda is another product of the chlor-alkali process along with chlorine. So we measure NaOH in the IR, so we don't use our OMA or TLG or anything like that. That's one of our other products, I would say. And then another chlorine application would be measuring hypochlorite and bisulfite in water effluent. So a way to clean sewage water is to chlorinate it, and the way they do that is they add sodium hydrochlorite. But what that does is it produces chlorine as a byproduct in the sample. So then they add bisulfite to that water, or sodium bisulfite to that water, which gets rid of the chlorine. So in this water treatment process, it's not quite a chlor-alkali process, but in this water treatment process, measuring hypochlorite and bisulfite are great applications for us as well. And then again, you can see more of the plant diagram, and we'll share this presentation with whoever's present right now, so they have this information available to them. after. Some more applications by industry. You have the petrochemical and polymers industry. So first off, you have measuring TBC and 1,3-butadiene. Basically what this is a polymerization inhibitor. So basically a butadiene is a monomer and you're storing it and you don't want it to polymerize. So what you do is you add TBC, and what we do is we measure the TBC in butadiene. I've also seen TBC in styrene or toluene or toluene or something like that. So measuring polymerization inhibitors is typically another good application for us. MEHQ and acrylonitrile is a good application. Ethylene glycol would be a color application, so that would be a physical parameter like I was talking about at the beginning. That would be the same with MEG, UV transmittance. So we cannot measure MEG concentration as it does not absorb where we need it to, but we can measure the purity of it or the transmittance of it. This is pretty common. It's very, very straightforward application for us. Like I said, transmittance is just measuring the amount of light that successfully passes through. So there's a little less to it than measuring, say, a chemical concentration. Also in EDC and VCM production, good applications for us would be measuring chlorine gas, FeCl3, and moisture. We have plenty of these applications with Olin and Dow. I forgot to mention, but we have many of those high percent chlorine with OxyChem, Occidental Chemical Corporation in Texas. And yeah, we have a bunch. We have a lot of those moisture analyzers in EDC with Olin and Dow. And then these final 3 bullet points you see here are different color measurements. We can also, these 3 chemicals, benzene, styrene, and toluene, also all absorb in the UV. So it is possible for us to measure these things. It's not always ideal, as there could be some cross sensitivity somewhere, but say you have a lab measurement or something like that, or so your research on one of these, it does absorb, so we can theoretically measure it. And then in this next slide, I added another plant diagram for EDC and VCM production. So you can just see a couple more applications, applied analytics applications through a process. Again, let me know if you want. I have a bunch of these plant diagrams, so let me know which ones you guys are most interested in, and I will be sure to get those to you. Next would be our applications in natural gas. So our applications in natural gas are more downstream. I would say definitely downstream. So at odorant stations where they're adding mercaptans or THT or whatever odorant they use, we're good at measuring those mercaptans or THT or any of the odorants. We can also measure H2S. That's another common application in natural gas downstream. And BTX, so BTX or your aromatics, we can measure. We measure that slightly differently than how I showed you with the full scale and multi-component analysis. We use it more, we measure that more like a photometer would, but it's still totally possible. We just sold a BTX and natural gas to BP just last week, I believe, so. So that's pretty much it for our natural gas applications. And these are just some common applications. These are not by any means all of our applications. Let me know, ask me what you want to measure and maybe we can do it. Some other common or good installations we have are measuring metal ions like iron or copper or cobalt or something like that. And then there's also TiCl4, so tickle we call it, which is basically we measure that in a chlorine vent gas. That's another good application. Some other good SEMS applications exist out there, like we can measure H2S and SO2 and emissions monitoring. Moving on. So far I've only really talked about the applications we have in the UV vis range using our OMA and our TLG. We also have an IR analyzer, which I'll get to later, which that's what allows us to measure moisture and CO2 and CO and things like that. But I'll get more into that in a bit. So what you see here, basically on the left is the OMA with the flow cell, and on the right, what you see is the TLG with a UCP on the right, which would be the utility control panel, which would control your steam utilities, your instrument air, your nitrogen that would be used to, say, flush the probe or something like that, or purge the analyzer, or control the steam that's used to remove the sulfur vapor in the purge, which I'll get, or in the probe, which I'll get to later. So you can see there's the analyzer portion, and then the flow cell is always outside of that analyzer. In the tail gas probe, the flow cell is housed right in the top of it. And then in the OMA, you can see that flow cell is external. Typically that would be in a sample conditioning system. So you can, condition your sample beforehand to control as many things as possible. It looks like these are stainless steel ones. The OMA is typically standard carbon steel. TLG is standard stainless steel 304. But the reason that we separate the flow cell from the analyzer is basically just to separate wetted parts from materials. Many times the samples that we're dealing with are toxic or corrosive or even deadly. So we want to keep the sample away from human contact, and we also want to keep it away from the very expensive electronics. So what we do is we just keep the sample. We bring the light to the sample instead of bringing the sample to the light. So the fiber optic cables connect those carrier light beams. Those are standard 1.8 meter. For tail gas, we go up to 10. For some other applications, we can only go up to 5 meters, but that's application dependent. So here we'll go over some of the components. I've already touched on a few of these. But so you have the xenon light source, which is 5-year lifespan. And that goes into the fiber optic cables, and it hits the collimator, which focuses the beam through the flow cell where it interacts with the sample. And the diode array, which is basically your detector. So you have the xenon light and the diode array are in your spectrometer. Then you have the flow cell, and your fibers connect those. Let's see, what else do you have here? And then on the right, you can see the OMA, or the analyzer portion. That's actually the TLG, sorry. You can see on the left side of that, there's a purge that looks like an X purge. So I don't know if you guys are all aware what purging does, but it just doesn't allow air from ambient air to come into the analyzer, which is a form of protection on the analyzer. You can see the HMI in there, which I already talked about briefly. Next slide. It comes in, sorry, go back. This is the wall mount that you see here. It also comes in a rack mount, and there's a portable option. The portable option has less customizable options, I would say. That's very application dependent. So a lot of people want, a portable analyzer for their wellheads, but that is not an option because wellheads are very variable. You never really know what's coming out of those. And our analyzers you do need to know sort of the stream composition in order to make a measurement. So if there's variability like a wellhead, that's not ideal for us. And then moving on. So this slide shows our main components, which is the spectrometer, which is basically your detector. Our standard spectrometer is UV vis 200 to 800 nanometer wavelength range. We also have the SW-NIR, which allows us to go a little bit higher. And we also have an IR detector, which allows us to go up to, I think, 2,500 or something like that. But I'm sorry, I don't have that written down. And then also we have the HMI, which is run by Eclipse software. It's Windows 10 embedded operating system. There's auto zero, so that will protect the analyzer against any drift or anything like that. Auto zero happens every 6 to 8 hours, depending on customer preference. There is manual span check. So the span check is necessary to verify your measurement. This is the auto zero is what keeps the accuracy and the resolution of the measurement, but the span check is what verifies the measurement. It's what validates it. You know, so it's what tells you that the analyzer is reading correctly. So span check is done, again, depending on the customer. You know, we recommend every other month. Some people do it every month. Some people do it every week. Some people don't do it. So that's a customer thing, really. So the spectrometer communicates with the HMI via Ethernet cable. The spectrometer is your detector, and your HMI is basically your way of seeing those values and what your detector is reading. Next. So here's a video, which I hope will work. Just talking about the OMA, which is our most customizable analyzer. It's what we use to measure if a chemical absorbs in the UV range, then we use the OMA and we customize the OMA or calibrate the OMA to measure the chemical that you want. Just hold on a second here.
Graham, and I'm one of the field service engineers here with Applied Analytics. We'd like to take just a little bit of your time to demonstrate the OMA 300 UV-Vis process analyzer. The OMA 300 offers a uniquely robust approach to solving some of the most common analytical demands in the oil, natural gas, petrochemical, and pharmaceutical industries. The OMA 300 has a wide range of analytical capabilities, including hydrogen sulfide, mercaptan, sulfur dioxide, ammonia, and chlorine, just to name a few. Moreover, our process analyzers can monitor these components in a myriad of different mediums, including but not limited to crude oil and natural gas. Inside of an OMA 300 process analyzer, like this one right here, are several important components that work together to provide accurate, real-time concentration readings of process compounds. Let's take a look. The OMA 300 utilizes several main components to achieve different analytical demands, namely a human interface unit, or HMI unit, the Nova 2 UV-Vis spectrometer, fiber-optic cables, and a flow cell. In real time, these components operate to provide the uniquely characteristic spectrum of each desired process compound, which is then used to accurately determine each component's concentration. During normal operation, signals of white light pulse from a xenon light source. The signal travels via a fiber-optic cable to the entry point of the flow cell, where the light beam is narrowed through a collimator lens. Here, the signal radiates directly across the flow cell path length, interacting with the continuously drawn process sample fluid flowing inside. Now containing the distinct absorbance imprint of desired chemical components, the signal exits the flow cell on the opposite end through a collimator and travels via a fiber-optic cable back to the spectrometer inside of the analyzer enclosure. The light intensity spectrum measured by the detector is processed by the analyzer's HMI unit. The absorbance spectrum is calculated and visualized by plotting lost light intensity at each wavelength due to the process sample interactions. Because absorbance spectra are uniquely characteristic to each desired component and are directly proportional to the component's concentration, the OMA 300 can output these concentrations of the process sample fluid in real time. From xenon lamp to diode array, the entire cycle occupies a few milliseconds and involves no moving parts. Applied Analytics has become a mainstay in the oil, natural gas, pharmaceutical, and petrochemical industries by applying this very effective and reliable approach to process analysis. If you have time, please check out our video on uniquely customized sampling conditioning systems, as well as other videos on more specific applications. Thank you for taking.
Okay, so that was a nice little video my buddy Graham put together a year or two ago. That talks about, the OMA. It talks a lot about what I said and visualized it pretty well, I think, for you guys. So I wanted to add just some customizable options. You can't quite see it here, but you can add a heater with a PID, you can add coolers, you can add things like that. So you can install the analyzer really anywhere. You can install it in very hot or cold environments. There's customizable materials. All that's never really an issue. Hazardous areas should never be an issue for us. We have ATEX, ICEX, UL, Zone 1, Zone 2, you name it, it should be fine. So that's a little bit about our OMA process analyzer. And then next we have a TLG, but I don't think we really need to watch this video. So I'll talk about the Mr. Probe a bit, which is kind of what this video was going to do for you in the next slide. So here you see a very nice cutaway of the internals of the Mr. Probe. So you can see the bottom of that would be stuck into the process pipe. And you can see the flow path follows those yellow arrows up the probe body. And you can see the blue section, which we called a cold finger. And what the cold finger is doing is dropping the temperature, which allows the sulfur vapor to condense and drop out back into the process pipe. So that's basically how we remove the sulfur vapor. I don't know if you guys have any experience with tail gas analyzers, but removing sulfur vapor is very important, and it's a huge concern for operators. So we do it right in the probe. We don't use demister pads, which I've heard some operators don't like. We just use a simple heat exchanger. And then so you can see the sample then continues up into the flow cell C to D, where there's more steam being brought into the head of the probe, so nothing condenses. Mainly here, we don't want moisture to condense because that can get on the lenses, which will affect the measurement. And the sample then flows down the other side of the probe body where it hits a junction where there's an aspirator that's constantly motivating flow. And then the sample is then just put right back into the process pipe. So that's pretty much what the demister probe is doing. It's our patented demister probe. We're very proud of it. We think it works really well. It does work really well. There's a blowback steam function or nitrogen function, which would flush out any condensed sulfur out of the probe neck. So if you're wondering if condenses and drops down, there is a way to keep the bottom of the probe clean by a blowback function. And in the next slide, you'll see sort of a representation of the separation of wetted parts and electronics, with more specifically with the tail gas analyzer. So you can see the wetted parts are all in the probe. The sample just goes up and down the probe, and the measurement is made right in the head of the probe. Like I said, you don't want to come in human contact with these samples, and you don't want it to come in contact with like your expensive electronics. So the probe is totally steam driven. There's no electronics in the probe. And yeah, so that's a major safety precaution of ours, is the separation of wetted parts and materials. Here I will briefly discuss our products that are not the OMA or the TLG. One of them being the infrared photometer, the IR photometer. So what we do here is we measure moisture, carbon dioxide, carbon monoxide, methane equivalency. Those are some common ones that we measure with the IR photometer. And what this does is basically allows us to have better bids on projects where, say, you want to have an H2S and a CO2 measurement we can provide one analyzer to do those by adding the IR photometer into the sampling conditioning system of the OMA, so or something like along the lines of that. We also have, I don't see it on pictured on the side, we have an APG 700, which is used to measure hydrogen. That's another good one of ours. We have an O2 analyzer. It's only fit for general purpose. Again, it's kind of an analyzer that allows us to bid on more projects than others. It's not one of our main products. And here you can see what the rock mounts sort of look like. Here shows a TDL, which we use for low ammonia measurements, low ppm ammonia measurements. We would typically measure ammonia with the OMA for percent level or high ppm or something like that. But we had a lot of customers coming to us with low ppm ammonia applications, so we developed TDL, and that's what we use for that. Here you can see a bunch of different images of sampling conditioning systems. Basically what we're doing is we're controlling the sample's pressure, temperature, density, phase. You know, say it's a natural gas sampling system. Sometimes we need to use aromatic traps to take out or get rid of the aromatics, so there's no cross sensitivity with the H2S measurement, you know, anything like that. So this is just showing you a bunch of different, there's a few drawings you can see in there, and then there's some actual images. But they're all sampling conditioning systems with which we offer with all of our analyzers. You know, sometimes customers want to go somewhere else or go through an integration company for the sampling conditioning systems, and that's fine. We still offer it. It's just part of what we do. You know, most of the samples that we deal with need to be conditioned. You can't just take it out of a pipe and measure it. You have to control the variables, like I said. So just to wrap everything up, some benefits of our products. We can measure up to 5 chemicals at once. So like I had that multi-component analysis slide, you can deconvolute a total absorbance into different chemicals. You can't always do the 5 chemicals, say you ask for, but theoretically, with our software and our spectrometer, we can measure up to 5 chemicals with one analyzer. The separation of wedded parts in electronics is something unique of ours. It's what we consider a benefit. We like the design of that with using the fibers. It's very compact and lightweight compared to competitors. I wish I had the exact dimensions and weight, but it only needs, say, the demister probe, you only need it, one person can lift it. All you need is a drill to install it. It's very easy to install. It's very compact, lightweight. There's very low maintenance, which we like to boast about on these things. They don't need a lot of attention at all. And there's not a lot of spare parts needed. We do our best to keep everything as simple as possible while still getting the job done. So there's not a lot of spares needed. And that pretty much wraps up my presentation. If you guys have any questions or comments or anything at this time, I'd be happy to answer them. Same with Carlos.
Pues muchas gracias por escuchar a Brendan Brady de Apply Analytics. Cualquier pregunta o comentario es ahorita buen momento para postearlos en la aplicación. De igual manera tenemos aquí invitados presentes, si alguien quiere presentar algo, les comunica. Ok, pues muchas gracias por haberse inscrito. A todos se les va a enviar una copia de la presentación para su información y para su evaluación. Estamos a sus órdenes. Cualquier pregunta, comentario o manera de contactarnos es metiéndose a nuestro sitio web, sicamedición.com.mx, y estamos a sus órdenes para cualquier necesidad de atención. Muchas gracias.